Welcome back everyone to the Business Intelligence and Analytics course. This week we are going to talk about regression.
In the past we discussed about descriptive analytics. We discussed about what happened. We analyzed the data that we had, we cleaned it, we performed SQL queries on it, we did summary, we calculated the summary statistics. All these are ways of understanding what happened in the data that we already had. Now we move to a more exciting part. We move into predictive analytics. Here we are going to use the data that we had in order to predict what will happen in the future. In particular, with regression, we are going to predict numeric values. So this is the flow of data-driven decision making. We have identified the business problems that we had to solve. We found the data that we needed to collect in order to answer these questions. We have pre-processed the data, we have cleaned it, we have removed missing values, we have normalized the data. And now we move into stage 4 and 5, where we prepare the data for learning, for data mining and for machine learning. So the first step is going to be also some part of small pre-processing, splitting the data into train and test sets. We will describe later what this means. But most importantly, we are going to develop the models for doing some predictive tasks. So today we are going to deal with regression. So regression is an instance of a supervised learning algorithm. So we said we have two big classes of algorithms. We have supervised and we have unsupervised. Unsupervised is something like clustering, where we don't give the labels or the values that we would like to predict. And we'll see why regression is an instance of a supervised learning algorithm. So it's an instance of a supervised learning algorithm because we are given a set of features for the objects that we are monitoring, be it customers, products, etc. And also the numeric value that we want to predict. So this is essentially the label. That's why this is a supervised learning algorithm. So imagine that we are given here many actually rows of our data. And these are three features, three columns that we have, three values that we monitor, 10, 100, and 12. This can be anything. I just abstract here. And for this we say, okay, given these three numbers, the output is 15. This output can be anything. It can be the number of products someone bought, it can be the value of some product, etc. So we are given many examples of this that we have collected from the past, that we have from our business. So given this, it gives that. Given this, it gives that. And then what we want to do is, given a new object, which has possibly different these three values, what would be the numeric value that we want to predict? So this is what we are going to do with regression. This is the problem that we essentially solve. Applications. There are many applications of this, just a few here, and we are going to see many more later. We would like to predict the price of a house, given how big it is, the square meters, how many bathrooms it has, does it have a pool or not, is it close to a busy street or not. This is an instance of a regression problem, predicting the price of this house. Another example, given a set of features for a car, this is an Aston Martin, the size of the engine, the weight of the car, the aerodynamic factor, what is the mileage of this car, how many are the kilometers per liter of gas that this is going to go, how far is it going to go, given a lot of other examples that we use in order to build this model. Now let's recall some terminology. The type of data that we have, we said it has to be in some kind of structured relational format. And here we are going to have many of these features. In this case, we monitor customers, whether they are female or male, how many dependents they have, or if they have dependents, if they have a phone service or not. So each one of these rows here is one observation. An observation can be a customer, can be a patient, can be a car, a country, a novel, a drug, a movie, anything. We have columns. So each of these columns, we are going to model it, we are going to give the name of small x, lowercase x. In statistics, these are called the independent variables or the predictors. The set of all the features that we have, it will be represented with capital case x, or the features that we choose to represent each of the entities. And then we have one column that we would like to predict. So this is a numeric column in a regression. It is a number. And this we call the target variable. In statistics, we call it a dependent variable. Right? So we have x, as many of those as we choose. It might not be everything. Let's say I choose to have 3 only columns. We're going to call this x. And the one that we want to predict is going to be the y. Here, given these 3 columns, I would like to predict how much will the total charges be. Now, what we want in general is to create a model for doing this prediction. There are many ways to create this model. Today, we are going to see how to do it with regression. We'll start with a motivating example. Suppose you want to sell your house or your apartment. How much are you going to sell it? This is the question here. One way to solve this problem is to see what were the past prices that apartments or houses were sold, select some set of features, and based on that kind of extrapolate and say, okay, I believe my apartment or my house should be sold for this price. For sake of simplicity, in the beginning, we assume that we just collect one feature from all the houses that we have monitored, and this is how big they are, the house area in square meters. So this means that this apartment that was sold was 120 square meters. And the price is 930 francs or dollars or anything. Right, so we collect many of those. And what we do is, if we want to see this visually, we can plot, we can create a scatter plot. So on the x-axis, we put the square meter. So this is our big X. These are all the features that we use in order to do our prediction. And on the y-axis, we actually put the y value, right? This is the target variable, what we want to predict, which is going to be the price. And these are all the points, the data points that we have. So for every data point, imagine we had 120 and 930. This might correspond to, let's say, this point here, 120, and this is the price, 930. Okay. Right, so we put a point for every row of this matrix. And what we would like to do is we would like to estimate this variable here, or this function here, right, this one. We can use any model to do that. It can be linear, it can be more complex. For now, we are going to assume that it is linear. So what we would like to do is we would like to build this regression model. So we would like to learn this function, which is, of course, never going to approximate all these data points accurately. That's why it's going to have also an error. So what is a good model here? What is a good function? We don't really know what is a good function. So it might be the average value. This is the average of all the values, of all the y values that we had. It might be a linear model, so we estimate a linear model. It might be a quadratic model here, or it might be a higher order polynomial in this case. For now, we assume that there exists a linear model, so this case, and we would like to approximate it. So we are never going to find this optimal f of x because we don't have at our disposal all the house prices in the world. So we just, given the few data points that we have, we are trying to approximate it. We are going to find this f hat. This small symbol, we call it hat, this f hat. And we are going to learn this from the limited amount of data that we had. Right? This is why we have this distinction, because we never have the full data set in order to learn this f of x, this optimal function. Right, so you might learn this orange function here, which is pretty close to the optimal one. So what we should always recall is this very nice quote that all models are going to be wrong, but some of them are going to be useful. This is a very nice quote by George Box that you should always keep in mind. Whatever we are going to compute, the model that we are going to estimate is always going to be wrong because we are always going to have errors in the measurements, in the data points that we have, etc. But if this model is useful, if we can use it to make some useful deductions, then this is going to be good. Alright, now so let's move further. This is how we are going to build this model, our predictive model. We are going to get again this example from the houses. We want to predict the sales price of a house, how much we can sell our house. This is the y variable, the target. We are going to collect a lot of this data, and we are going to collect many features: the house area, the area of the lot, the number of baths, etc., etc. So we are going to get this data. From some of them, we don't have to use all the features, so we can use some of these columns. We're going to do a feature extraction, or we are going to generate some new features. For the simplest case, let's assume that we just use one column, so the house area, and we also keep the last column, so we're going to keep this and this column. We are going to split it into two sets, the training set and the test set. I will give more details why we do that later. But this is one of the most important things that you should learn in machine learning, that you always split this data. On one part of the data, you learn the model, so you find the linear model using some part of the data, and you evaluate how good it is on the other part of the data that you have never seen. So this part of the data we never see, so we never use it for building our model. This is a very important thing, and this is the single most important slide that you should remember. We'll see more details on this later. So for now, let's focus on this first part, how to train and how to build this linear model. How can we do this? So imagine that we have these data points, again, the square meters of the house and the price that it was sold. We plot them onto 2D, and we want to find the line that goes through this data. Right, so imagine that this is the y hat. Again, I put the hat here because it's going to approximate the real function that exists. And since it's a linear function, this has this form, w0 plus w1 multiplied by x. So x is the value here. This is how big the house is in square meters. So I want to find this and I want to find that. If I have these two parameters, then I can completely describe my linear function. The w0 is called intercept. The w1 is called the slope. And these are the parameters of the model. So when we say in machine learning, I want to learn a model, it means I want to find these parameters. In this case, we have two parameters. So these are the regression coefficients. Now let's remember a little bit. If I have this function in general, f of x is w0 plus w1 multiplied by x. Imagine that I have this function 1.5 plus 0 of x. So the w0 is 1.5 and the w1 is 0. What does this represent? This represents, of course, a straight line, because no matter what value I give here to the x, I always expect to get 1.5. So this is a horizontal line. Now if I have another function, f of x is 0.5 of x, how would this look like? In this case, the w0 is 0 and the w1 is 0.5. This will look like that, meaning that it will pass from the 0, 0, and it's going to have some particular slope. And finally, if I have 1 plus 0.5x, how is this going to look? This is going to look like the previous one, but it's going to be higher by 1. Right, this is easy to see. If you put 0 here, right, so the 0 here, it should pass from position 1. Right, this is just a review of how a linear function works, given a particular slope and given a particular intercept. So this is the slope, this is the intercept. Good, just a quick quiz for you. If I have this function w0 plus w1x, what is this point? Choose one of the three. Is it w0, is it w1, or is it minus w0 over w1? What do you think? In order to find what is this value, you notice that here I have a x of 0. So you can put x0 here. If you put x0, this gets eliminated. So the position here is what? Is w0, comma, or 0, comma, w0. And how about here? What is this point here? Obviously, this point has a w of 0, sorry, a y of 0. And if we have a y of 0, if you set this to 0 and you solve the equation, what are you going to get? You are going to get that x is minus w0 over w1. Right, so this data point here is the minus w0 over w1, comma, 0. Now, assume that you have found this line somehow. How good or bad is your model? This you can estimate by calculating some error function. The error function in this case is the so-called residual sum of squares. So given these two parameters of my model, the w1 and the w0, the residual sum of squares is how every point, how distant it is from the line that I have calculated. I get this value and I square it. I square it so that I make it positive. Right? So we get for every data point, the sum here means that for every data point, I get what is the y value of this data point. So how high is it from here, right? Minus how high is it from the estimation, from the linear model. So this is the difference here. And this difference I square in order to make this positive if it's above or below the line. Right, then I sum all of these values up, and this is the total error that I have. So for every value, so this is the sum of house 1, assume this is house 1. What is the price of house 1? This is the price here. And from this I subtract the estimation that I have, this value here, which this is the estimation, given the house area, multiplied by W1, and I add the intercept, I get this difference, and then I square it, right? This square should be outside here. Right? There should be one more parenthesis here. Right, so I sum all of this, and this is the total error. This is called the residual sum of squares. Now we haven't discussed how to find this line. How do you find this best line that minimizes this sum of squares? This is the best one. What you can do is you can try many values for this and see which is the one that has the lowest error. This is the best one. But how do you find? Do you just try randomly many of them? No, you don't. So in order to find the best line, you do a method called gradient descent. This is an iterative method that tries different solutions and goes, so it guides these tries of W0 and W1 based on the error. So if we see that the error increases, then we try some different values. We don't go into that area. We're not going to cover how gradient descent operates, so we are going to assume that using Python, using the package that we are going to explain to show you, sklearn or scikit-learn, this is going to return the optimal linear function that gives the least error. If you are interested, you can attend the master course in data mining and machine learning, or if you cannot wait and you want to explore how gradient descent works, you can watch this YouTube video here. However, for now we are going to assume that we have a black box, and given the data, it's going to give us back the W0 and the W1. Right, so it's going to find this line that minimizes the error across all the points that we have observed. All right, this is a demo, if you want to see, of gradient descent. So you start from some position, this can be random, and then the line is going to progressively go, it's going to go slowly at the end, and then it's going to finally get to the position that minimizes the error. And it's going to give this, one of these is the W0 and the other is the W1 here. They're called M and C. Right. Now, after we have this line, imagine that we have found this line that goes through the data and minimizes the error, this linear function. This is the one that gives the lowest RSS score. Now we can make predictions. If we have this line, we can predict what is the price of a house, let's say with an area of 100 square meters. How can we do that? We can go to the place where it is 100, right? We can simply replace the x with 100 here, and we're going to find that a price for an apartment or a house with 100 square meters should be around 788 francs. So we go here. This is the value that we are going to predict. Of course, if you have this equation, you can also do the reverse. You can also ask questions, okay, if I have a house which is sold for 1.2 million, what is the expected area for that house? So here you can put the 1.2 million here and solve for x. I'm going to leave this as an exercise. This is going to give you the area of the house, which is sold for 120, or at least the expected area, how big it's going to be. Now, how do we interpret this coefficient? So the W0, the slope, This is the intercept and the slope. Intercept and the slope. What is their meaning? So W0, of course, is the value of y if we give x for 0. So it's the predicted price for a house with 0 area. So this is not very meaningful in our example, at least. So for something that is 0 area, what is the price? Now, the W1, what is it in this case? It's the predicted change in house price for 1 unit change in house area. So this means that if I go from 100 square meters to a house having 101 square meters, what is the additional value that I should pay for this additional 1 square meter? Right, this is reflected here. If I go from 100 to 101, what is the difference in the price that I should pay? This is the difference. I go from here to here. What is this difference? In order to find out that this is actually the case, you can do this as an exercise at home. You can get W of 101 minus, y of 101 minus the y of 100. And you are going to see that what you end up if you subtract these two values is actually W1. Right, I'll leave this as an exercise for you. The goodness of it, you can also estimate using the R-squared coefficients, which is typically used in statistical analysis. Right, if you have an R-square value of 1, this is a perfect model. It captures perfectly the variance of the original data. If you have an R-square value of 0, this is a very bad model. And how is this computed? So the R-square value is 1 minus the RSS that we computed before, so the residual sum of squares, over the TSS, which is the total sum of squares. This is the sum of the values minus the average of all the values that we have, that we want to predict, squared. If you want to see this visually, this is the TSS. So we get the average of all the values, and for each one of the y values, we get the difference, right, from the average value, and you square it. Essentially, this is the area, the square, right? So this is the area. And we get all of this, and we sum them up. This, that, and the other. So this is for 4 data points. And the residual sum of squares is visually represented as that. So we represent it as a square, right? Because we have a square. It's essentially the square that is being formed from the data point to the line. So if we sum up all of these areas, this is what is the RSS. There is another way to compute the goodness of it, which is using the mean average error, which is computed with this equation. So we get the absolute value of the difference to the line, and then we get the average of this. So 1 over n if we have n points. And this MAE, the mean average error, can provide some more meaningful numbers compared to the RSS. So if the mean average error is 25,000, this means that on average we are off by 25k in our prediction. Whereas the RSS depends on how many points we had. So if you have more points, the RSS is always going to increase. Right? So the mean average error provides some more meaningful numbers. And now we're going to see an in-class demo using sklearn and Python for how to predict house prices. So just click on this link here and we can do this demo together. Let us try to open the link. If you open it, you are going to end up in this Python notebook inside Colab. If you want to run it also, you have to click here on the Open in Playground in order to open it in your space. Let's minimize this for a second. And now if you start pressing Shift Enter, you are going to execute the different text or code areas. Here you can say run anyway. This was authored by me. It is pretty safe. Here we load a similar dataset as the one examined in the slides. It's a dataset of houses, different features for houses, and also at the end we will see there is this sale price, how much it was sold. For simplicity, let's select the features which we called X. We just select one of them in order to create a one-dimensional regression. So this is the first floor square footage. This is the X, and the Y variable or the target variable is the sale price. We can review the data quickly and to create a linear model in sklearn. So we are going to use sklearn or scikit-learn. This is a pandas, a Python notebook. It is very easy. We just use these three commands. We import the linear regression from this Python library. We say, okay, we want a linear regression. This is the model that we want to create. And then we call fit on the data that we have selected, on the X and the Y. To the predictions, we use the predict function on either one or many values. And now if we plot both the original values, the blue dots, against the red line, so the red line is the linear regression that we have computed, we can visualize the result. We can also import different metrics, like the mean average error that we saw, or the R-square metric, and we can plot the value. Finally, we have some exercises where we add more features and we retrain the model just to deepen your understanding. Welcome back. Previously, we saw how to learn this linear regression, how to create a model of linear regression using one feature, one column, and one output. Now we are going to see how you can add more of these features, or that it is possible to add more of these features, which is called multiple regression. So we have seen how to use the house square footage or square meters in order to predict the price using this linear model that we have learned. We can of course add more features if we add another dimension, another feature, which is the number of baths. So this might be 1, 2, or 3, etc. We can see that immediately we have points in the three-dimensional space. So now we are not going to learn a line, but we are going to learn a surface, which minimizes this RSS error. So this would be the definition of the line. So we have again W0 coefficient, W1 times X1, so X1 is the square footage or the square meters. And we have also W2 multiplied by another coefficient which we want to learn. So this is the number of baths. So what we would like to learn, with this linear regression is these three coefficients, W0, W1 and W2. Right, the square footage, the number of baths. And of course we can also add, as we saw in the example in Colab, there are many other features that we can use. We have the house area, it can be the lot area, number of bathrooms, the number of bedrooms, the year that it was built, etc. The list is endless. In the end, we are going to have, let's say, we choose 4 dimensions. So we choose the house size, the number of rooms, the number of bathrooms, and the land size. In the end, we attach what is our target variable. So this is the array that we create. In practice, what this model that we are going to train adds is also this column here of ones. So this is going to be represented in a matrix format somewhere in the computer. So this is going to be the first column, the second column, the third, and the fourth. So this is your X, capital X variable. And implicitly, the model or the algorithm that you have is going to add these ones. So these ones correspond to the X0. What we want to do is we want to learn the weights W0, W1, W2, W3 in this case. Right, so if we multiply this, and probably we have another one as well, W4. So if we do this matrix multiplication, right, we want approximately to get this value, right? This is essentially the set of equations that we are solving here, right? You don't need to worry so much about this, as this is the internal representation. But just to show that in addition to having one column, you can also add many columns, and then you expect maybe to minimize, to have a better or worse error. Now let's see some examples of linear regression, or multilinear regression. This is a very useful paradigm. So one example would be to determine your salary. This is again something that is numeric that we would like to predict. How much salary will you get after you graduate? This is a very important question for you. So the features that you can add here, the columns, let's say, so the X would be your total grade. Would you get a grade of 5.5 or 5? This may affect your salary. Or how many internships that you do. Did you do 0 internships? Did you do 1, 2, 3, etc.? The years of past experience that you have from previous jobs, the number of friends on Facebook. This is very important, as this represents your social network. If you are very sociable, you are more likely to find a job. This is the assumption. Or the number of people you connect in LinkedIn, etc. How do we formulate this as a linear equation? So we have this, which is your salary, depends on W0 is the intercept, and it depends on your grade, on your experience, the Facebook friends, the number of Facebook friends, the number of LinkedIn people that you know, and you have to determine these coefficients here, W0, W1, W2, W3. So you start giving a lot of data from many people, grade 5, experience 2 years, Facebook friends 100, LinkedIn friends 200. For another student, grade 5.5, experience 0, number of Facebook friends 300, LinkedIn friends 1000, etc. And what is the salary that they get? Here you are going to fill this in. And for a new person, you are going to give these values and you are going to try to estimate what it is going to be. So this is an example of linear regression. Another thing that you can predict is the stock price. Again, this is a numeric value. How much will the stock price of Facebook be tomorrow or in the next month? This depends for the next day on the last day's value, on the last week's slope, how many events in the news we had about the company, how many times Donald Trump mentioned the company in his tweets. Or another example, to predict the number of retweets, how many people are going to retweet your post. This depends on your followers, the number of hashtags in your post, the text, the number of images, and so on. So all these are the x1 to xn parameters that you have. Now we move into the evaluation. Now let's move into evaluation. How do we check how good our model is? We said, of course, we have these different metrics. We have the RSS metric, we have the MAE metric, we have the R-square metric. However, the value of this should not be estimated only on the data, on the full data set that you have, that you train the model. So this would be erroneous to do, and this is the most error that most of the people do when modeling data, when trying to build a model based on the data. So they use the full data that they have, and then they evaluate again how much is the error on the full data set. This is wrong for machine learning. And this is wrong because, like that, you don't know how your model is going to behave on new data. So what you should do is, from all the data set that you have, carve out a small part of it, which we call test dataset, test set, and we only test the prediction error, any of these various metrics, only on this part. So we use the first part just to train the model, this part, and we use the second part, so we use this part just to train the model, and we use the second part to test the model. Right? This is the well-known train-test split. Now let's see how you do it in practice. So you do this because you don't know exactly what the future will bring. Nobody knows, actually. So if you want to give a realistic measure of how good or how bad you are going to do, this is a way of doing it. Instead of waiting for more data to come, with the data that you already have, split it into two parts. Usually we do this 80-20 split. 80% of the data we use to train the model, and the rest 20% we keep to test how good the model is. So imagine that this is the whole dataset that we have here. What we do is the following. We keep randomly 80%, let's say, I give a number here, of these rows, which we use to train the linear model. So we use it to train the linear model. And then the other 20%, for example, we keep to test the model. So this is called the held out dataset because we never see it, we never use it to train the model. We just use it to test it. So imagine that we have this green line, which is the model that we have created, right? This green line is the model. It's not linear here, it is maybe quadratic, but it doesn't play any difference. So imagine that these blue points are the 80% of the training set. So these points, and the gray ones are the gray ones here are the test points that we have never seen. So we use these points here to find what our model should be. In this case, we find that it should be this. Right? We can also calculate what's the training error, but we don't, this is not very useful. And then, sorry, here, this should be test error. So we use the points that we left out here, 1, 2, 3, 4, in order to test how good or bad our model is. And we do this for all of the test examples. So we assess the prediction error using only the test set. And this is in order to get a more realistic, again, view of how good or bad our model is going to be. We can only do this by testing on data points that we have not already seen. Typically, we do an 80-20 split for train and test sets. This means that we use 80% of the dataset for training the model, that is for learning the parameters W, W0, W1, W2, etc. And we use 20% as the test set for predicting the model accuracy or the model error. How we do it? If we have the whole dataset, we shuffle the rows, right? So we randomly shuffle them around. Then we can get the first 80% of the rows as the training set, and we get the last 20% as the test set. So it's important to reshuffle everything in the beginning. So if we have this, we reshuffle it, and then we take the first 80% and the last 20%. There is also a concept called cross-validation, and this is a way of getting even more accurate estimates of the prediction error. Now, why do we do cross-validation? And I will explain what it is in a minute. So if we use only the test set, if we use only one test set, so we said we split the data into this part and this part that we test, we may get good or bad prediction results depending on what this test set was. So the data points that ended up here may have been good, may have been bad. In order to get a more realistic estimate of the prediction error, it is quite advisable to do many test sets. How to do it with a dataset with only this dataset that we have? This is the way that you do it. So typically, if this is your whole dataset, instead of doing just one split for test and for training, so the whole thing here, what you do is you split your dataset in several parts. Let's assume in this case that we split it in 5 parts. 1, 2, 3, 4, 5. Each of these parts is called a fold. So this is the first fold, the second fold, the third, fourth, and the fifth fold. And now what we do is we conduct various experiments. So in the first experiment, of course, in the beginning we have to shuffle the rows of the dataset and then we split it. What we do is we get the first part, the first fold, and we use it, keep it out for the test set, and we train our model on all of these folds, on the second, third, fourth, and fifth. From this, we are going to get some estimate of the error. Let's call it error 1. Then, for the second experiment, experiment 2, we use this as the test, the second fold, and we use 1, 3, 4, and 5, all of them together, in order to train. From here, we're going to get an error 2. And understandably, we get, if we do 5 experiments, we get 5 errors. Error 5. So the error of the model is the average of these errors, the average of all of them. So this gives us a little bit more accurate estimate about the error. Since we don't just do one test, we do 5 tests in these cases. Usually we use a K of 5, so we use 5 folds or 10 folds. So we repeat the experiment many times using different train and test sets, and we average the errors that we get. Now some practical considerations in order to make your model behave better. As we said, in order to find this solution, there is underneath, under the hood, an algorithm called gradient descent that it is used. This algorithm may not work well when the features do not have the similar or the same range of values. And in our example, this may happen. So if we use the house area, this may range between 20 and 350 square meters or even more. The number of bathrooms, it is much smaller. It may be between 1 and 5. So what happens in this case, this you don't need to completely understand, as this relates more to the inherent of the gradient descent. If these are the two estimates that you want to estimate, W W1 and W2 of your coefficients. If you have values which do not have the same scale, so this is represented here like that, you are going to see that your algorithm is going to oscillate a lot and it's not going to potentially find the good solution. Whereas if you rescale your values in order to have the same range, you're going to see that your algorithm is going to behave much better. The practical consideration for you, what you keep in mind, is that for every column that you have in your dataset, for every feature, it's good to have it in a range between 0 and 1. Or at least have all of them the same range. If you want to put everything within the range of 0 and 1, you can do it with this equation. So you can subtract the mean value of the column, and then you can divide by the range of max minus mean. Another normalization that you can do is the so-called mean normalization. So here, you remove the average value of the column, and you divide either by the range or by the standard deviation. If you divide by the standard deviation, then you have 0 mean, so your column is going to have a 0 mean, all of these values if you sum them up, and the unit variance. Alright, this is an example of how this is going to work for an area of the house. So I encourage you to go and do all of this. Of course, doing the rescaling in scikit-learn, which we are going to use for our labs, is very easy. You import some packages and then you call just one function. You don't have to actually implement all the nitty-gritty details of doing the rescaling. Another thing for practical consideration, how to handle categorical variables. Up until now, we assumed that the features that you have, your columns, were numerical. The number of square footage or square meters, the number of bathrooms, the area, the lot of the area lot, or the lot of the area of the lot. Many features, however, in your datasets are going to be categorical. How do you deal with those? In this dataset of where I'm trying to predict some value, there is a column called gender. Obviously here this can take two values, male and female. So if it only takes two values, and these are categorical, then you can simply convert it into 0 and 1. And you assume that, let's say, female is 0 and male is 1, or vice versa. So this is a very easy way of converting this categorical column into numerical. If it's binary, convert into 0 and 1, or 1 and 2, it does not really matter. Now, how to handle categorical variables, like in this case, the payment method, which take more than two values. Here it can take the value of electronic check, mail check, bank transfer, credit card, etc. Let's assume for now that it takes 4 different values. We can use a method called Hot Encoding. What we do here is for every different value that we have, if we have 4 different values, we expand, in essence, this column into 4 columns. One for payment method when there is with electronic check, one for payment method when there is a mailed check, one when there is a bank transfer, and one when someone paid by credit card. And we put 1 if the value here is electronic check. Here it is electronic check, we also put 1. Here it's electronic check, we also put 1. And all the other rows, we put a value of 0. We do the same thing for the other columns. Here there is 1 and 1 because there is mail check and mail check. 0 in the rest of the rows, and so forth. So this is the hot encoding. So when your column has more than 2 values, this is what you can use. Another method is to simply add a numeric representation for each of these different values. So if there is electronic check, I add 1. If there is mail check, I convert this into 2. if there is bank transfer to 3, etc. So this is called label encoding. As a rule of thumb, when should you use one or the other? And this is just a guideline. When there are, let's say, not a lot of distinct categorical values, 10 up to 10 or 15, we use one hot encoding. If there are, let's say, 100 distinct categorical values, then it's better to use label encoding. Otherwise, you are going to end up with many features, with many additional columns, which is going to penalize your performance when you do the learning of the model. In practice, you don't know which one is going to work the best, especially if you have, let's say, up to 20 distinct values in your categorical column. So you should try to do both and see which one gives the lowest test error. This is the method that you should use. If you want to see an example of this, you can have a look here in Kaggle, how to handle categorical variables. Again, categorical encoding in sklearn, you can use two functions, one hot encoder or label encoder, and this is going to solve your problem. So what we discussed today was regression. We saw that with regression, you can predict numerical values. We introduced linear regression as a very simple predictive model, and multilinear regression if you use multiple columns as your features. We discussed training error and test error. You should always estimate how good your model is using the test error and not the training error. You can also make your estimate of the error more robust using k-fold cross-validation. And we discussed how to handle categorical variables or columns using either one hot encoding or label encoding. So this concludes our lecture for this week. I hope you enjoyed it and you are going to get more hands-on experience in the labs that you are going to have.